Alright, so let's say again that in order to solve a second order linear differential equation with constant coefficients, first we need to set up the characteristic equation, and we know what to do if the roots of the characteristic equation are real, which happens whenever the discriminant b squared minus 4ac is positive. We don't know what happens, how to deal with it if the discriminant is negative, right? So here is an example. But so let us just try to see what is going to happen if we just try to, use the complex roots, right? So according to the general recipe, we know that if the complex roots are I and minus I, then we should try to solutions of the form e to the power it and e to the power minus it. So let us try to substitute them into the ODE and see what's going to happen. Right? So if we have e to the it, right? So if y1 equals e to the it, then y1 prime is going to be, well, just according how we usually differentiate the exponential function, is going to be I times e to the minus it. Then y1 double prime is going to be what? So when we, plus here, of course, plus. So when we differentiate the second time, we just multiply by I one more time, so it's going to be I squared e to the it, and I squared is minus 1, so we are going to get minus e to the it. And now y1 plus y1 double prime, which is the left hand side of the ODE, is going to be e to the it plus minus e to the it, which is going to be 0. Check. So the function e to the it still satisfies the differential equation. So the only problem is that it kind of it is a complex valued function, but it still satisfies the differential equation. And we are going to make use of this fact. I mean, so now I just verified it for a particular differential equation, but of course it's going to be the same thing for well, in a general situation, right? Because simply the same calculation that we did for real valued exponential functions, if we just let the constants r1 and r2 to be complex numbers, it doesn't change anything. So all the formula are still going to be valid, right? So in other words, we are still going to have a solution of the form a linear combination of two exponential functions, only now the two exponential functions are going to be complex valued exponential functions. But now we are going to make a certain trick. So we are going to use this Euler's formula in order to convert two complex solutions into two real solutions. That's what we're going to do. I will show you how it works in a particular example. And although it is a specific example, but if you change y6 and 25, the coefficients here, to a, b, and c, in general coefficients, it's not going to affect the logic. So which means that although it is a specific example, generally speaking, we are going to have the same thing whenever in any situation when the discriminant of the characteristic equation is negative. Right? Okay, so let me write down the characteristic equation here is r squared plus 6r plus 25 is 0. Right, so the discriminant here is b squared, which is 36, minus 4ac, so minus 100, which is negative 64. So as expected, it is negative. So it means that the two roots are r1 to r minus 6 plus minus square root of the discriminant is 8i now, where I is the imaginary unit, over 2. So now we are getting minus 3 plus minus 4i. Okay, so it means that the following two functions, y1 is e to the power minus 3 plus 4i t, and y2, which is e to the minus 3 minus 4i t. So these two are two solutions of the given differential equation, and the only problem is that they are complex valued solutions. So now we are going to do a very clever trick. So we are going to think how we can combine them, how can we construct a linear combination of these two solutions that is free of this problem, that is a real valued solution. And in order to do it, we need to use the Euler's formula, right? So according to Euler's formula, the real part of the exponential of the exponent can be taken out. So here I'm going to have e to the minus 3t. That's the real part of the exponent. And the imaginary part of the exponent, which is 4it, is going to transform into the combination of sine and cosine, right? So we are going to have cosine 4t plus I sine 4t. Well, but then in the same way here, I'm going to have e to the minus 3t, which is taken out, times cosine of, so let me write down cosine of minus 4t plus sine of minus 4t. Well, but cosine is an even function, so which means that this minus can be deleted. And then I'm going to get just cosine of 4t. And sine is an odd function, which means that this sine can be moved out here. And here is what I get. Alright, so these are the two complex valued solutions of our differential equation. Well, although they are complex valued, but notice that they look very similar. So they have the same real part, and the sorry, I forgot I. There should be an I here. And the imaginary part is just the negative of each other. So in other words, these two solutions are complex conjugates. But then you can extract just the real part by a linear combination. Right, so let's try it. So how can we extract the real part of the solution, of the first solution? So we need to take 1/2 y1 plus 1/2 of y2. And then when we add these two solutions together, then since they have the opposite imaginary part, it's going to cancel out. So we're going to have I sine 4t minus I sine 4t. So the rest is just the real part, which is e to the minus 3t times cosine of 4t. But the imaginary part can be extracted in the same way. So the imaginary part of the say the first solution is going to be 1 over 2i y1 minus 1 over 2i y2. Well, indeed, if you subtract y2 minus y1, so then cosine 4t is going to cancel out, but sine 4t is going to survive. We're going to have I sine 4t minus I sine 4t, so which means plus 2i sine 4t, and then when we divide by 2i, then the rest is just sine 4t, so then we'll get e to the minus 3t sine 4t. But take note that the original y1 and y2 are linearly independent. Right? So that's how we constructed them. And then we have these coefficients, the matrix of coefficients. So we took two linear combinations of y1 and y2, and what we get is going to be linearly independent whenever this matrix of coefficients is non-degenerate. So let's verify that it is indeed non-degenerate. So let me write the matrix of coefficients and compute its determinant. And then, so this is needed to ensure that the two new solutions are going to be indeed linearly independent. And so the matrix of coefficients is 1/2, 1/2, 1 over 2i minus 1 over 2i. We need to calculate its determinant. Is going to be minus 1 4i minus 1 over 4i, which is minus 1 over 2i. The important thing is that it is non-zero, which means that the matrix is non-degenerate, and therefore these two solutions are again linearly independent. And therefore, so what we got is that the general solution can be constructed as the linear combination of these two solutions, which are linearly independent. Because of what we just discussed. Alright, of course, now I just explained the particular example, but the general situation is going to be the same, because, well, our explanation did not really depend on, the exact values -3 and 4. So, which means it is going to be true for any second-order differential equation where the characteristic equation has complex roots. So hence we get this theorem. So two distinct complex roots means that they are complex conjugates, actually. So they're conjugate to each other here. And since they're conjugates, it means that they are of the form real part plus minus I times the imaginary part. And finally, let me notice that this expression here, b squared minus 4ac, is negative, right? And since it is negative, it means that square root of a negative number is actually, so maybe let me write it like this, minus b over 2a. So that's the real part, and then plus minus, this is going to be actually square root of 4ac minus b squared, which is positive, over 2a times I. So that's another form. Alright, so here our lambda is minus b over 2a, and our mu is square root of 4ac minus b squared over